It started as a small tick on a computer screen, a tiny wiggle in a long line that usually stays calm. No one in town felt it, no dishes fell, no windows rattled. But the seismometers, the machines that listen to the earth, heard something. At first it was nothing new. Mount Rainier wakes sometimes. Mountains move, the ground breathes, that is normal. Then the wiggle came again, and again. A rhythm formed, small quakes pulsing like a slow heartbeat. They came every few minutes, the same pattern, over and over. The US Geological Survey watched the pattern grow. They compared the data with other events. Nothing matched. Not the usual volcano rumbling, not ordinary earthquakes. So the USGS did something rare. They raised the alert to the highest level. Not because smoke rose, not because lava poured out, because something deep under Mount Rainier was happening that scientists could not explain. People living near the mountain felt a cold knot in their stomachs. Mount Rainier is a giant. Millions live near it. If it wakes in a bad way, it can be very dangerous. This is the story of what happened next. The science, the fear, the search for answers, and the race to keep people safe. It began on a Tuesday morning. The seismometers recorded a thin blip. A few hours later, more blips stacked up. By midnight, the blips had become hundreds of small shakes. The first surge lasted nearly 2 days. Sensors showed tiny quakes deep under the peak. They were not loud, they were not strong, but they were many. Thousands of tiny quakes. Local people heard nothing. Dogs did not bark, the ground did not snap. The only place anyone could see the change was on screens in the labs. Then the pattern changed. The tiny shakes began to pulse in a steady rhythm, every 10 minutes, then every 7, then every 5. The pulses came like regular beats. Seismologists call this kind of repeating signal non-typical. It did not match normal volcanic tremor. It did not look like a normal earthquake swarm. The pulses spread, they moved lower and then higher. They shifted east and west. The mountain seemed to be speaking in a patterned voice. Over the first week, instruments recorded more than 10,000 small events. Some sensors farther away picked up echoes. Satellite data picked up a tiny change in the ground surface. The mountain had shifted by millimeters. Not enough to see with a human eye, but enough to tell scientists something big was moving deep below. The USGS raised the volcano alert to the highest level. This did not always mean an eruption, but it did mean, pay attention, be ready, watch everything. Mount Rainier is not just a mountain, it's a giant of ice and rock. It wears huge glaciers. Those glaciers sit on volcanic rock. If the volcano heats quickly, ice can melt fast. Melted ice plus loose ash and rock can make lahars. A lahar is a wet, fast-moving flood of rock and mud. It looks like concrete moving down a valley. Lahars can travel many miles and bury towns in minutes. More than 80,000 people live in areas that could be hit by lahars from Mount Rainier. Cities like Puyallup and Orting sit on old lahar layers. Highways and rail lines cross lahar paths. Rainier's last major eruption was long ago, but its history is full of sudden, violent floods. That is why the USGS watches Rainier closely. Small signs could mean big danger. People who live here know the signs: sirens, emergency alerts, practice drills in schools. But the alert in this case said, we do not fully know what is coming. Prepare, watch, stay close to official updates. The mountain's size and the glaciers make Rainier different from many other volcanoes. That is why even small changes can matter a lot. At the Cascades Volcano Observatory, a team works 24/7. They listen to the ground, they watch satellites, they read wind and gas. When data changes, they talk. When the first pulses showed up, the team ran checks. Could the sensors be broken? Could some passing truck make the signal? They tested gear, checked power, and called other stations. All equipment was fine. The data was real. The team called the USGS in Colorado and other volcano centers. They discussed models and scenarios. They ran simulations. The data did not match a normal magma rise. It did not match a simple hydrothermal event. The rhythm was puzzling. Raising the alert to the highest level is not done lightly. It is a message to emergency managers, to utility companies, and to local towns. It means, get ready. Make sure warning systems work. Prepare shelters and evacuation routes. Officials in nearby counties read the message and set plans in motion. They checked sirens, updated phone alert lists, and tested emergency responses. Schools reviewed plans. Hospitals checked backup power. People in town watched the news with concern. For some, It was the first time they felt the mountain might be dangerous again. The repeating pulses under Rainier were the strangest thing. They were not earthquakes caused by rock breaking. They were not the long hums from magma moving. They were a different animal. Scientists called them episodic pulses. They looked like a machine beating rhythm under the mountain. The speed of the beats changed over days, sometimes faster, sometimes slower, but the pattern held. Researchers looked at many possible causes. Hydrothermal fluids, boiling water and steam can move in patterns, but those usually make noisy, messy signals. These pulses were too regular. Magma resonance, a big chamber of magma can create standing waves, but magma moving up would also change surface heat and gas. The gas reading stayed calm. Tectonic triggers, distant earthquakes can trigger local events, but there were no strong quakes elsewhere that matched the timing. Then a new idea appeared: resonance. Resonance is when something vibrates in step with another force. Think of a tuning fork. If the right sound hits it, the fork vibrates. Could Rainier be resonating with some unseen force? Some models showed that the magma and the rock could set up a resonance at certain frequencies. If something tapped those frequencies, the mountain might hum. But what could tap it? A series of tiny shifts in pressure deep below? A slowly moving pocket of fluid? Or something we have not thought of? No single idea solved the puzzle. The rhythm remained a riddle. When a mystery appears, different scientists offer different ideas. Each idea gets tested, discussed, and sometimes argued about. The Rainier event started a big debate. Theory A: hydrothermal movement. This idea says water and steam under the mountain are moving in regular ways. Hot water can boil and bubble in pockets. If those pockets are in a ring, they could beat like drums. Evidence for this: small gas shifts and shallow quakes sometimes match hydrothermal activity. Also, Rainier has hot springs and a complex water system under its glaciers. Evidence against this: the pulses were too regular and too deep for normal hydrothermal systems. Theory B: magma resonance. Here the idea is that a pocket of magma deep in the earth is sloshing. That slosh can create repeating signals. It might not mean magma is going to reach the surface. It could just be moving in a deep chamber. Evidence for this: deep quakes and ground tilt could hint at magma movement. Evidence against this: no increase in surface heat, no gas surge, and no outward signs of magma motion. Theory C: telesismic or planetary wave. This idea is stranger. Distant earthquakes or even large ocean waves can create waves that travel through the planet. These waves can nudge sensitive systems. If the mountain is tuned just right, a small nudge could make it vibrate in a pattern. Evidence for this: some large distant quakes have caused small effects on faraway volcanoes. Evidence against this: there was no matching distant quake at the start. Also, the pulses continued in a way that did not line up with known outside triggers. Theory D: something new. Some scientists whispered about a new type of event, something not in the textbooks. New instruments might be needed to find it. This theory is the hardest for scientists to accept, but it cannot be ignored. When data does not match any model, sometimes science learns something new. The debate continued. Each week, more data arrived. Some theories fell away, others gained small support, but no single theory explained everything. While seismometers watched the mountain's pulse, satellites kept a different watch from space. Using radar and GPS, scientists can measure ground movement down to millimeters. That is smaller than the thickness of a penny. That is the power of modern tools. When they checked Rainier, satellites showed a tiny outward motion in one area of the mountain. Later, the motion reversed. The mountain breathed out a little, then pulled back. The timing matched some of the pulses. That told scientists one thing: something was moving material underground. Not a lot, but enough to nudge the surface. Other satellites checked heat. Thermal sensors saw no big warming. Gas sensors in the air saw no big increase in volcanic gases like sulfur dioxide. Cameras saw no steam columns. So whatever moved, it did not reach the surface in a dramatic way. It was deep, and it was subtle. That made the event more puzzling. If magma was rising, the surface would likely show some heat or gas. But if an elastic rock layer shifted or a fluid pocket moved deep below, surface signs could be small. Scientists built new models. They tried to match deep fluid movement to the millimeter shifts. Some models came close, others failed. The mountain continued its odd pulses. Word of the alert spread fast. Local governments could not ignore it. Even with many unknowns, they had to be ready. Emergency managers called meetings. They checked lahar sirens and evacuation routes. Churches offered shelters. Schools ran drills. Businesses checked insurance and backup plans. In Orting, a town in a lahar path, people remembered the old stories. Grandparents told children about thick mud flows in the past. People packed small bags with water, flashlights, and warm clothes, the items families might need to leave quickly. Social media filled with worried posts. Some shared official updates. Others spread rumors and fear. Officials worked to keep messages clear. Stay calm, make a plan, follow official updates, and do not spread rumors. News teams came. Cameras filmed the mountain and the people below. Reporters asked tough questions. Officials answered as best they could. For many, this was a reminder that nature can change fast. For others, it was proof that science can warn us before danger arrives. And for a few, it felt like living through part of a story they had only read about in books. Scientists do not only use machines, they use history. The memory of other volcanoes helps them know what to watch for. Mount St. Helens exploded in 1980 with little warning to the public. People saw an avalanche, then an eruption that changed the mountain. St. Helens showed how fast things can go wrong. Other volcanoes have confused scientists too. Sometimes long, quiet periods are followed by rapid changes. Sometimes unusual seismic patterns precede eruptions. Sometimes they do not. Rainier has its own history of big events. Old layers of lahars are stamped into the valleys. Those layers show that powerful flows happened before. People built towns on top of older flows because the land was flat and fertile. That is how life and danger often meet. The past teaches caution. It reminds officials to plan for worst-case scenarios. It also reminds people that living near a volcano has always been a balance between danger and the bounty the land gives. As the pulses continued, scientists brought in more help. They placed new seismometers on different flanks of the mountain. They lowered instruments into small boreholes. They tested gas filters and ground-penetrating radar. They ran controlled experiments. They modeled fluids moving in cracks. They used supercomputers to test thousands of scenarios. The new instruments added detail. Tiny tremors that earlier sensors missed now showed up. Deep signals that once seemed uniform now had structure. Some pulses had higher energy, others were nearly silent. One new instrument detected a slow, low-frequency wave beneath the mountain. That kind of wave can travel far and can set up resonance in rock chambers. It gave new life to the resonance theory, but still did not prove it. Some teams focused on gas. If magma rises, it releases gas. New gas sensors measured air near the mountain every hour. Most readings stayed normal, but occasionally tiny blips of sulfuric compounds rose. Too small to point to an eruption, but enough to keep scientists watching. No single instrument solved everything, but each added one more piece to the puzzle. The mountain slowly revealed more of its secrets, a little at a time. Fear has a way of spreading fast. People feel it in their bones. Even when officials say the danger is low, worry grows. Local small businesses worried about customers staying away. Schools planned longer drills. Emergency shelters checked stock. Volunteers offered help. People talked about their families. Parents asked if their children were safe. Grandparents remembered old warnings. Some said prayers. Others searched online for tips on how to survive a lahar. The community pulled together. At the same time, helpers came forward. Geologists stepped up to speak at town halls. Scientists explained data in simple terms. That helped calm some fears. There was also care for mental health. Panic can harm people as much as real danger. Local health centers set up hotlines. Churches and civic groups offered counseling and comfort for those feeling overwhelmed. The mountain brought neighbors closer. People shared supplies. They checked on elderly neighbors. They made plans to help one another if the worst happened. A strange event at an American volcano was not only local news. Scientists around the world watched the data. Volcano monitors in other countries compared their systems. What happens under Rainier might help them understand similar signals elsewhere. Some countries offered help. International teams with special sensors volunteered to come. Data flowed in. The world gathered around the mountain through code and satellite links. For many, the Rainier pulses were a scientific gift and a warning. Science learns fastest when many minds work together. Sharing data speeds discovery. After 3 weeks of pulses, the pattern intensified. The pulses came faster. More sensors lit up. Satellite data showed a slight bulge in one flank. The USGS tweeted updates. Governors and county officials studied options. People felt the mountain's breath in new ways. Schools stayed alert. Some events were canceled. The public was asked to stay calm but be ready. Officials prepared for possible scenarios. Lahar paths were cleared, sirens were tested, evacuation routes were marked with orange signs. But at the same time, no order to evacuate was given. The threat was real, but uncertain. That is a hard place to be. The week felt heavy. People waited for new data. Scientists worked day and night. The mountain's pulses did not stop. Then a new instrument found something different. It detected very small magnetic pulses in the ground near the mountain. Magnetic readings pulsed in time with the seismic signals. This was surprising. Changes in magnetic fields can come from moving fluids, changing temperatures, or even electric currents underground. The match of magnetic pulses and seismic pulses pointed to a linked process. Scientists proposed that conducting fluids, salty water with minerals, might be moving in cracks and creating tiny electrical currents. Those currents can create magnetic changes. If the fluids move in a patterned way, they could cause both magnetic and seismic pulses. This finding brought new hope. Maybe the rhythm had a cause that could be studied and predicted. If fluids are moving, engineers might be able to model their path and the risk. But the magnetic pulses were tiny, and instruments must be carefully checked. Scientists confirmed the data in multiple ways. The pulses were real. Now the team had seismic, GPS, satellite, gas, and magnetic data. The picture was richer, but still not complete. With more data, scientists began to sketch a model that fit many observations. 1. Anomalous pulses. Repeating seismic signals come from deep regions where fluids and rock interact. 2. Fluid movement. Saline, mineral-rich water moves in cracks, making small currents and magnetic pulses. 3. Resonance. The geometry of rock chambers can amplify small shifts into repeating pulses. 4. Surface response. These deep changes cause millimeter shifts on the mountain's surface. This model tied many threads together. It did not prove everything. It did not mean the mountain would erupt, but it gave scientists a working idea they could test. The model helped predict which sensors should light up next. Scientists tested the prediction. Some sensors behaved as expected. Others did not. Science is a slow climb toward truth. Each test either makes the model stronger or forces a new view. Modern technology gave scientists power they did not have decades ago. Drones flew over zones hard to reach. Fiber-optic cables laid in boreholes listened to tiny tremors. Machine learning looked for patterns humans might miss. AI helped sort millions of tiny signals and find the repeating beats. It could tell which pulses had different signatures. That saved time and pointed scientists to the most interesting data. But machines do not replace human judgment. They point. Humans decide what to study more. People still check the data with old-fashioned logic and careful experiments. Together, machines and humans made progress. The mountain's puzzle slowly unfolded. What were the possible outcomes? Scientists prepared 3 main scenarios. Low risk, pulses fade, the system settles, no big change happens, sensors calm down, life resumes. Medium risk, fluids continue to move and cause small surface changes. Some small landslides or minor lahar flows in steep valleys could happen, but not in major towns. High risk, a sudden change melts ice near hot areas, creating lahars that travel down main valleys. That could threaten towns and roads. Officials planned for all 3. They prioritized the safety of people and infrastructure. Preparing for a worst case does not mean it will happen. It means being ready. Many lives are saved by careful planning. During the alert, stories spread of neighbors helping neighbors. A woman shared blankets and packed extra supplies for an elderly neighbor. A farmer offered his truck for fast transport. School bus drivers practiced new routes. These small acts are powerful. They show how communities can rise together when nature tests them. At the same time, rumors and fear circulated on social media. Officials asked people to rely on verified sources. Community leaders stepped up to keep messages calm and helpful. After 6 intense weeks, the pulses changed. Their rhythm became less steady. Some sensors quieted. Others still pulsed, but less often. The USGS lowered the alert one step, not to all clear, but to a slightly less urgent level. That move was cautious. It did not mean the mountain was safe forever. It only meant the most active phase had eased a bit. People breathed a little easier, schools resumed normal activities, businesses reopened, but many kept emergency kits close. The mountain had shown its power and its ability to surprise. Even now, months later, scientists still ask big questions. Was the main cause fluid movement, resonance, or a mix? Could a later pressure change restart the pulses and push the system into a different state? How well can we predict similar events at other volcanoes? The Rainier event taught scientists that volcanoes can behave in ways we do not fully expect. It also showed the value of modern tools and community readiness. Scientists keep working. New instruments stay in place. Satellites check every day. Machine learning watches for new patterns. The mountain may sleep, or it may surprise us again. The Rainier pulses taught an important lesson. Earth still holds mysteries. We can learn more by listening closely, sharing data, and preparing together. The USGS will keep updating the public. They will warn when danger grows, and they will study the mountain until the puzzle is better understood. Mount Rainier is part of this land. It gives water to rivers, shapes the soil, and draws visitors who love its slopes. It also reminds us that Earth is active and alive. Science gives us tools to read that activity. It may not always give immediate answers. Sometimes it gives new questions, but each step helps us stay safer. Communities can be ready without living in fear. Planning, simple gear, and clear information make a difference. We learned something important from the USGS alert. Watchfulness matters. Listening matters. And when nature speaks in a new voice, we should listen with care. If this story mattered to you, please stay informed. Subscribe to this channel for regular updates on Mount Rainier and other Earth stories. Click the bell so you get alerts the moment new information arrives. Share this video so your friends and family near the mountain know what to do. Science moves faster when we all pay attention. Community safety grows when we work together. Thank you for watching. Stay safe, stay ready, and join us as we keep listening to the Earth.